Disk stalls or block storage failures are very common in every cloud, and it's something that our customers have also recognized from the disks that back their CockroachDB clusters. To give you an idea as to how common disk failures are, Backblaze, the popular cloud storage platform, were replacing a hard disk every 30 minutes in 2023. There's nothing to say that the next hard disk won't be yours. Write-ahead log failover allows CockroachDB to self-heal from disk stalls. Let's have a look at some diagrams to give you an idea as to what's going on under the covers. When you make a write to CockroachDB, the write enters a mem table, an in-memory table, and the write-ahead log at the same time. There's one write-ahead log for each mem table. Once a write has made it to the write-ahead log, it can be considered committed, and the mem table will eventually flush the data to the SST files, which is where CockroachDB stores data. And what we'll be doing today is working in a Kubernetes cluster and simulating disk stalls using ChaosMesh. I'll have 3 CockroachDB nodes running across 3 Kubernetes nodes in a GKE cluster in GCP, and I'll be using write-ahead log failover to automatically recover from disk stalls. Without write-ahead log failover, if this disk were to stall or slow down for any reason, CockroachDB would have no other option but to keep on writing to that degraded disk, ultimately degrading the customer's experience of the platform. With write-ahead log failover, you introduce a failover disk, which can be around 10% of the size of the primary disk, and in the event that the primary disk were to stall or slow down, CockroachDB would automatically recognize that and start writing to the failover volume. When the primary disk comes back online, it repoints back to the primary disk and everything continues as normal. I already have a Kubernetes cluster, and now I'll install CockroachDB into the cluster. My configuration for the CockroachDB cluster is very similar to any Kubernetes demo you've seen before, but this one harnesses write-ahead log failover, which looks like this. I have an additional volume mount, which I've just called failover. That could be called anything. And I mount it to the cockroach/cockroach failover, again arbitrary, directory in the pod. When starting the node, we provide a write-ahead log failover path, which directs to our failover volume, and any configuration that we want to provide to the write-ahead log. Mine is simply a config map, which looks like this. Your configuration values might differ from mine, but this is a good starting point. Let's install CockroachDB and run some chaos experiments. With the cluster initialized, I'll fetch the external IP of the public service, which is currently pending, and I'll make that available in each of my terminals as an environment variable. Let's connect to the CockroachDB shell. There are 2 main settings to be aware of when configuring write-ahead log failover. The first is max sync duration, and that defines the maximum amount of time that any disk operation should take before triggering either a log entry or a crashed node. And you can configure this behavior with the max sync duration fatal enabled flag. Set it to true to crash the node, set it to false to trigger a log. And the second is write-ahead log failover unhealthy op threshold. If a write-ahead log write takes longer than this threshold, write-ahead log failover will trigger. By default, without write-ahead log failover, the max sync duration value is set to 20 seconds. This results in the node crashing early if a slow disk is encountered, allowing the other nodes to take up the leases and continue operation. However, when you want to enable write-ahead log failover, set this to a higher value to give write-ahead log failover a chance to kick in for that node before it's crashed. A good value for write-ahead log failover is 40 seconds, and that's what I'll configure now. The default value for write-ahead log failover unhealthy op threshold is 100 milliseconds, and I'll leave that as is. We can see that, however, from a call to show cluster setting. Now let's hop on to the CockroachDB console and configure a custom dashboard to help us monitor what the write-ahead log failover is doing. Go to Advanced Debug, Custom Time Series Chart, and we'll configure our first chart. The first value we'll grab is the raft process log commit latency. I'll go for P99.9 and I'll select per node store. This will show the write-ahead log commit latency for each of the nodes, and it will show it in nanoseconds. I'll add another chart and I'll configure it to show the amount of time that we've been writing to our primary data store. That's the non-failover volume. Again, I'll enable it per store, and it looks like this. It will carry on going up the longer we write to the primary store. Ideally, with no disk stalls, this value will just continue to rise. However, in the event of a failover, we'll start writing to our secondary disk. Let's bring in the metric, enable it per store, and that looks like this. Because we haven't failed over yet, we haven't written anything to the secondary store, and the duration, the amount of time that we've been writing to the secondary store, is therefore 0. And finally, I'll add a metric that increments every time we perform a failover switch, either failing over to the secondary or failing back to the primary. And as expected, that's currently 0 because we've made no failover switch. All of this data is available via the cluster API, and we can curl each of them to determine the primary and secondary stores. And for example, node 3 has a primary store of Cockroach data, as we configured, and a failover path of Cockroach failover. I'll create a table. This will be a simple bank account application. And I'll run a workload. This will perform a transfer from one account to another and will record the latency involved in that request. That's the total round-trip latency from my machine to CockroachDB and back again. And because my cluster is in the cloud and the operation needs to lock the rows, I would expect the latency to be within the 60 to 80 millisecond range. Now we'll introduce a disk stall, and we'll do that with this manifest. I'll target CockroachDB 0 in the CockroachDB namespace. I want to target the Cockroach data volume, the primary folder that CockroachDB is writing to, and any file in that directory, top level or otherwise, and I'll introduce 50 milliseconds of latency to every request that we make against that directory, and I'll do that for 2 minutes. With this command, I'll monitor the state of that chaos experiment. It's not created yet, so it's not finding anything, but as soon as I apply that, we'll see 2 things. This has gone to injected because I've injected the failure experiment. Notice that the latency hasn't increased from the client's perspective, but we've just made a switch. CockroachDB has recognized that the primary disk has stalled, or at least slowed, so it switched over to use the failover. Write ahead log failover has triggered. The commit latency did spike up to 360 milliseconds for a short period before coming right down again because we made that failover. The amount of time that we've been writing to primary storage has plateaued for node 1 because that's the node whose disk I stalled. And the amount of time that we've been writing to the secondary storage for that node is now starting to tick up. We'll wait for this to go back to not injected, and we'll take another look at the metrics. So that's just gone to not injected. If we come back over to here, the switch count will increase to 2, indicating that we've made a switch back to the primary storage. And there it is. Commit log latency continues to be steady, but now we're starting to see the uptick in primary write duration and a plateau of the secondary write duration. Let's disable write ahead log failover and introduce the same chaos experiment and see how CockroachDB handles it then. I'll delete the experiment and we'll tweak this configuration setting. This needs to be done very carefully. The current value of this setting is 100 milliseconds, and if you set it to a value higher than the previous setting we looked at, the storage max sync duration setting, that will disable write ahead log failover. Let's do that now. As I set the storage max sync duration to 40 seconds, I'll increase this from 100 milliseconds to 1 full minute. If we look at the setting again, we'll see that instead of being 100 milliseconds, it's now set to 1 minute. Let's inject that disk failure again with exactly the same settings as before. That's injected, but this time we won't see the switch. We won't write to the failover storage. We'll continue trying to write to the primary storage, and our latency won't be a simple spike and decrease. Coming back over to the client, we can see that it's experiencing latency because every single write to that first node can't execute in a reasonable time. The client is unhappy, and that latency will continue to be high until the 2-minute experiment window has elapsed. The client is experiencing latencies anywhere above 5 seconds, which is the point at which I give up and print out a context deadline exceeded message. Or at the very best, we're seeing average latencies of around the 500 millisecond mark. That's just finished. The experiment is no longer injected, and we're seeing the average latency coming down to normal again. The log commit latency will also come down, but this was only a 2-minute experiment. If the disk stall had gone on any longer, clients would have been affected for longer. The larger your CockroachDB clusters get, the more nodes they'll have, the more disks that will be attached, and the greater chances that you might run into a disk slowdown. I've just demonstrated the positive impact of implementing write ahead log failover for the disks that are attached to your CockroachDB nodes. We've gone from quite a serious production issue involving high latency and unhappy customers to a completely self-healing solution to the same problem. Write ahead log failover allows CockroachDB to recognize and recover from disk stalls and disk slowdowns. And it's another self-healing tool in CockroachDB's toolbox, turning very serious production issues into business as usual events, and another reason for your engineers not to be woken up in the middle of the night.